start this with CAD, this for rack and pinion model. So firstly we will try to do the partition here. So just I will pick up one node here and this line will be fine. Similarly, we just use some offset lines here. Okay, and then I will create my hex mesh. So I will choose this surfaces. This I am doing it roughly. Let me put 1 mm here. Let's see. So it will serve up my purpose. I am happy with this. I can further refine it, but for currently this is fine. Then for here, I'll just put this, and this I will control this edge. Okay, let me increase this to 4. Okay, this is fine. And then here, what I can do here is I can further do some coarse meshing here. Okay, this I'm happy with this. Then what I will do to generate the hex meshes, to drag this uh, elements, 3D elements, sorry, 2D elements. So I will click on this and I will attach all, and then I will use this node, sorry, this node, and my next, the end of the drag node will be this node. Okay, or 1 second, let me create some temporary nodes. Okay, here also I need to create. Okay, then I'll create one dummy element, dummy rack component. Okay, then I will just drag these elements. Okay, and then I will use this node and this node, and on this drag on the thickness direction I need uh, four elements, so I will use this drag plus, and the 4 elements are created. Okay, similarly, uh, I will now create one more component, which is my gear. Okay, then I will use this face elements, and then simply this node and this node, and on drag again I need 4 elements. So again I will use, 1 second, these 2 elements are fine, and I will use drag plus. So this is how uh, the 3D mesh has been created. Now I can delete this 2D elements as these are of no use now. Okay, once this 3D element is done, now I will create the properties uh, to assign, sorry, materials to assign it. Okay, so for this simulation, I'm just using the linear steel. Uh, so density I will assign as 7.9 e power minus 9. That is, by the way, tons. That is in my conventional unit, Newton mm and second convention. And then in plastic, I will do 21 e power 3, and mu will be zero point 0.3. Okay, then properties, I need to, as these are both hex elements, solid elements, I need to use solid section here. Okay, and material will be steel, and this both rack and pinion are of same property, that is property 1. Okay, so property assignation and material as assignment is also done. Okay, then the next step is, uh, we need something. Let me clear the temporary nodes. We need something to rotate this gear. So how can we do it? So for this, we will create one rigid. So rigid. So let me go to 1D rigids, and faces is there. So you can click on this instead of nodes. You can click on this faces, and then you can just do this. Okay. So uh, this node I can create it as set, which is load node. Okay. And this node I will just put this. Okay. Once this is done, what I'm what is the next step is to create a contact pair. For this, I'll go to this contact browser. You can go from view, and this contact browser you can check it. This browser can come. Then you need to create some surface element, that is contact surface. Then you need to create this contact surface. So this solid face is fine, this face is fine, and this I put 85 degrees for intentional purpose. So in one shot I can create the contact pair of this gear. Okay, once this is done, similarly I similarly I need to create one more surface, which is rack surface for the contact. Similarly, I will put more 85 here, and this I can even unselect this things. Okay. Yeah, up till here it is fine. I will my pin this gear will go up to here. Uh, okay, this is fine. Then once this is done, I will create one pair, contact pair. Okay, let me delete this. Okay, so this pair and this group, I am selecting this group, and this master I can select this master, and this property I needed. So I will create one surface interaction property. Okay, and then material, you don't need to fill anything. And then this surface behavior, as I am using my laptop to solve this, I will be using this as penalty contact, because this will solve easily in my laptop. If I have using a powerful system, then I may not use this penalty contact. This will ease the contact convergence. And friction, this I will put as hard. And friction, I will put it as, for time being, I will put a friction coefficient as 0.2. 0.2 is a generalized value between metals and metals. It is fine, I think. 0.2 is fine. Okay. Then in contact pair, I will use this surface interaction property, and adjust. I'm not using adjust option, and type I will put surface to surface, and this is fine. So contact is also defined here. It will come as groups here. Okay. Now I am I need to create one load step here. So I will go to utility step manager. I will need to create one step one. I need to create step one. Rotate. Okay. Then title, it's fine. You don't need to give it. Anal geom, that is non-linear geometry. You need to give it yes. Okay. Then these things are fine. And analysis procedure, you can go to static. Okay. And data line, you can go to initial increment. I want to give as zero point 0.1. Time, total time is 1.0, and minimum time you can give as 1e minus 5 is fine, I think, for this. Okay. Boundary, you can give it any load collector name. Then here, this load node, what I want for this load node, like it needs to rotate only about this z axis, and that is the only function of this gear. Other than that, there shouldn't be any movement. It shouldn't go in X, Y, and Z direction. It can't translate it in X, Y, and Z direction, and it can't even rotate about other axes. So it can only rotate about Z axis. So what I am going to do here is I will fix 1 to 5 DOFs. Okay. Then I need to provide some sort of uh, in sixth DOF, I need to provide some sort of angular some sort of angular displacement. I need to define it. So in sixth direction, I will define it as I can define it as maybe as yeah as displacement only. And then in sixth direction, I need to define it as I'm assuming that this gear will rotate about its own axis about 90 degrees. So 90 degrees, if I convert it, it is pi by 2. So pi by 2 is nothing but 3.14 divided by 2, which comes out to be, one second, which comes out to be minus 1.57. Why I use the negative sign, I'll show you. Because this angle, this uh, I want to rotate my gear about this plane, this one, and if I use positive, it will rotate in this direction, in positive Z direction by left, uh, by right hand thumb rule. So if you put minus, it will rotate about the negative Z. So this is how I maintain this rotation. Then once this is clear, this gear will only rotate. Now what about is this rack? The rack will move in x-axis only due to the rotation of gear. So we have defined the contact interaction due to that, so it will rotate. So it will translate about x-axis. But what about other DOFs? Other DOFs we need to fix it. So I will go again here. I'll simply go here and I will put this load collector, and then I will simply restrict this. So first thing first is like in it should not go in negative y. So how can I do it? I will constrain few nodes here. This node, three nodes are fine, or you can even take more nodes. Okay, and y I will constrain this y. Okay, now it should not even go in z axis also. Okay, so that I will fix this plane. Let me do this here. Sorry, z. Z is nothing but DOF free. So this second DOFs are free for the downward face, and its third DOF is free for this lateral face. Okay, and as anyways the solid are having only uh, translation DOFs, but that is 1 2 3. We need not to fix the rotation DOFs. Okay, then once this is done, what I need to do here is I need to define the output parameters, like output request, what I need from this analysis. So output request, I need to go to ODB, and you can write output 1, out 1, anything is fine. So out 1, and then I can just click on output. I need only field output. First is nodal output. I need the displacements, and I need the UR also, that is rotational displacements. Then other things I don't need it, and element output I need the stresses obviously. That is the only thing I need, and I need the strain also. That is the only thing I need. So this is fine. Once this is done, I think I'm pretty good with it. And let me export this then. So I will replace this file and let me export this. So once this export is done, we have performed a run, and then it got completed. So we will review our results. So you can see here, as it is working very fine here. If I play the animation, it is doing what is it expected to do, and you might see why there is delay uh, in the very last step. So I will show you the my HTA file. Actually, some after a certain point, it started taking very small steps, uh, increments in the per se, very small increments. That is why it is showing uh, very less uh, increment in the very last time. So that is how it is done in HyperMesh. So in ABAQUS CAE, same thing can be performed. So here I imported my property here, and you can see like the mass density. I put it 7.9 e power minus 9, and elastic property 210 MPa, and the point 3 it is there. Okay, in the same way you can go to here section manager, and you can see I defined a solid type as this rack and gear, and material is steel again. So it is the same material. Then again I can go to uh, this, and this section is nothing but this is the section assignment. Okay, and then there is no beam here and no profile. Okay, we will go to assembly here. Assembly is nothing but how we have assembled it. So it is nothing like translation and rotation. So how we can translate it? Suppose gearing in some other way, then how can we translate this? Then steps. So steps I have defined like initial. Let it be initial. I haven't defined initial. So time period is 1 second, increment is 100, and it will start at point 0.1, and minimum increment it can take as 1 e power minus 5, maximum it can take as 1. So other things are like it is a direct solver, as we haven't defined this, so it will take its default. Okay. Then we can go to here, which is field output manager. So field output manager, there are two types of output we have chosen: the nodal output, which is displacement and rotations, and there is elemental output, which is stress and strains. Okay. Then this is history output. We haven't requested any history output, so it will not show up here. Then we can go to interaction, where we have defined our contacts. So this interaction we have defined between uh, pinion and our rack gears. So this is the surface interaction we have defined it. So you can see there is a master surface, and rack is the slave surface. And finite sliding we have to. We haven't given any adjustment. Surface smoothing we haven't given. Clearance we haven't given. Okay, and this interaction we have given it. So to see the interaction, we can uh, go to here, and we can see this interaction. So we have given the coefficient of friction as zero. 0.2. Okay, and this penalty we have defined instead of frictionless or user defined contact. Okay, so now this is done. So this is constraint manager. We haven't performed any constraints, so this is fine. And then we can go to this loads. So loads. Uh, so this loads, we have everything here as a displacement boundary condition. So here you can see that I have put u is equal to 0 here, and where are others u is equal to 0. So this load node I have put the 1, 2, 3, 4, 5, up to 5 it is 0. Okay, and then in 6, DF6 it is 1.57 radians. So it is just radians. I am giving the rotation about 90 degrees. That is why I have converted to radians. As you can see, its axis is about this towards negative z. That means it will rotate about the negative z. Okay. Then we have it here is like the constraints. So u3. So u3, uh, that is z. So the faces which are perpendicular to z, I have put as 0 degree of freedom to 3 nodes in each face. Okay, because I don't want my rack to go here, to move here and here in z plane. Okay, and then finally the 8 BCs, which is nothing but I don't want my rack to go in y direction, so that is why I've constrained this. Okay, so once this is clear, uh, we can even submit the job from here. So that is how it can be done. So we have already solved here. So we will just view the uh, we will open the abacus viewer, and we will see how it is. So I will open this file in my abacus viewer, and we will see the animation here also. So those guys who are comfortable in abacus, they can also refer this. So sorry. So let me go to elements type, element sets. So this will have two different colors of uh, rack and pinion. Okay. So I will just animate this. So this is a nice looking plot, and this is how it can be done. Thank you.